All right, everyone. Welcome to another episode of the TWiML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Tom Goldstein. Tom is an associate professor at the University of Maryland. Before we get into today's conversation, be sure to take a moment to head over to Apple Podcasts or your listening platform of choice. And if you enjoy the show, leave us a 5-star rating and review. Tom, welcome to the podcast.
Thank you very much for having me. I'm a big fan of the podcast. I was really excited when I got invited to be on. I'm happy to chat with some about some of the things I've been working on.
Awesome. That is great to hear. And I'm looking forward to digging into our conversation about security and safety for generative models and beyond. But before we do that, I'd love to hear you share a bit about your background and how you came into the field.
Yeah, sure. So interestingly, my background, if you go way back, it's actually in applied mathematics. And when I got into the field, I got my first academic job was in a computer science department, and all my students wanted to do deep learning and machine learning, and so I started studying optimizers for deep learning because that was sort of within my field. And over time, I just started focusing on more and more mainstream topics. And one of the topics that really grabbed me is this issue of security and safety for AI. And I think one of the reasons why is just in at University of Maryland, we have a lot of security researchers, and I think just being in that environment, being around all the security researchers, being around all the excitement happening in deep learning, sort of a nice blend of things that I just started to get interested in. And over time, my research started to focus more and more on that area.
Awesome. Awesome. Well, introduce us to kind of your research portfolio. What are the things that you spend your time thinking about?
Yeah. So one of the things that when I started doing research on AI security, one of the early projects that I did was really focused on adversarial examples. We had actually a number of projects in that area, and I think when this field of AI security got started, the community really had a strong focus on this concept of adversarial examples. So
Yeah.
small changes to input data that have a large effect on the output of a model. Over time, I think the focus of the community has evolved a bit, and there's a much stronger focus now on things like data set privacy, which is something I've been working on recently. But if you go back and look at some of my older work, it's really focused on this area of adversarial examples. The main focus of my lab was actually trying to trying to study adversarial attacks in realistic situations and against realistic industrial systems. So there's a lot of academic work focusing on simple things like image classifiers, but I was really interested in whether or not we can identify security vulnerabilities in industrial scale systems. And so some of my early work was focused on attacks on industrial systems for things like object detection or content detection, so things like YouTube's Content ID. And also, we have some work that we did with some collaborators in the finance community on adversarial attacks on high frequency trading systems. And so those were the sort of applications that I focused on. One reason I like to focus on those applications is actually because I think the adversarial vulnerability of systems is greatest when they accept inputs in the purely digital domain. So a lot of adversarial example work is focused on physical world adversarial examples. So you try to create a thing that looks a certain way that can break a machine learning system. But actually, purely digital systems are much more vulnerable. So things like content detection, copyright detection systems, where you upload a video to YouTube and you can control every bit in the file that YouTube receives. And you can use that to create adversarial attacks. And so one of my students actually built a TensorFlow implementation of the Shazam algorithm for recognizing sound. And by making adversarial attacks against that system, we can actually make audio that is not recognizable as copyrighted. That's something that we are interested in. And like I said, we did some work on finance. Is it possible to manipulate high frequency trading systems by placing adversarial market orders? That's another thing that we worked on. And then I think one of the more high visibility projects we worked on was this invisibility cloak project, where we were actually building physical adversarial examples. We're trying to build clothing that you could actually wear that would make you invisible to object detectors.
And I still see examples of that kind of those products, like people building projects that purport some degree of invisibility to classifiers or object detectors. It seems to be still a popular idea.
Yeah, I think it captured the visibility cloak really captured people's imaginations. I was interested in it for purely academic reasons. There had been a lot of work on adversarial attacks on image classifiers. object detectors are much more sophisticated than image classifiers. And in fact,
Mm-hmm.
most object detectors, so what we call anchor-based object detectors, they actually have a separate classifier that looks at different portions of an image and tries to identify whether there's an object in it. So if you look at something like the YOLO detector, it actually tries to identify an object in about 20,000 different locations in an image. And if any one of those classifiers sees you, you're caught. And so fooling an object detector is very hard. And actually, there were some early papers that seemed to claim that you either couldn't create consistent adversarial examples for object detectors, or that it was just very difficult to do in general. And so I got interested in this problem. I just want to see whether we could actually build a system that would do it. And actually, one of the reasons I got interested in that project is because I was on sabbatical at Facebook at the time. And Facebook actually had, in the New York office, they actually had a printing lab for doing large format printing for printing posters. And I was looking for something I could do with the printing lab. And so one of the reasons this project emerged is because we actually went to this large format printing lab and we printed paper mock-ups of all of the clothes, and we would cut them out and we would glue them together, and we made all of these different prototypes for the clothes in order to get them to work. And so this was a huge project. It took a very long time, and we had to build a lot of different prototypes to make this work. It turned out the kinds of data augmentations that you use to create these adversarial patterns matter a lot. And we had to build an entire training pipeline for these adversarial patterns. So we actually used the COCO data set, which is an object detection data set, and we actually used gradient methods to learn an adversarial pattern that would remove every person from the COCO data set if you render this pattern on top of them. So we created an adversarial pattern that would essentially work on any person and in any position. And we did a whole bunch of mock-ups, and we made different alterations to our pipeline, and eventually we managed to converge to something that worked reasonably well against the YOLO detector. And now there's actually a bunch of companies that are selling these adversarial clothes. I actually had a store where we were selling them, was to raise money for my lab.
Oh, nice.
Yeah, we don't have that store anymore. And one of the reasons why is I actually don't like to endorse the idea that this is a reliable way to evade object detection.
Yeah, it seems like if it's something that you really care about, you know the consequences of failure could be dire.
Yeah, oh, exactly.
At least there's a class of situations where that's the case.
Yeah, and these there are situations and certain object detectors where these kinds of patterns work well, but there's also situations where they just don't, and it's not a reliable way to avoid object detection. Interestingly, when I was selling these things, I had a store where you could put the pattern on any item of clothing you want, and our most popular items were actually adversarial underwear and adversarial leggings. So I'm not sure that people were buying them to avoid object detectors. Maybe it's just because they thought adversarial examples look really cool. But yeah, I that was yeah. But I don't sell them anymore, and one of the reasons why is exactly that. I don't want people to buy them with the misconception that this is a reliable way to avoid detection.
And in this case, how sensitive to the model were the patterns that your method produced? Like, going from YOLO V1 to 2 to 3 to 8.
It's very very unpredictable. So, for example, an adversarial pattern trained on YOLO v2 would work fairly well on YOLO v3, but it wouldn't work very well on YOLO mini. And then you could transfer like across YOLOs. So, for example, something trained on YOLO might work on faster RCNN, but not vice versa. And it turned out it's actually incredibly unpredictable when these sorts of patterns will transfer across detectors. And actually, most of what the paper was focused on was studying the transferability across detectors and when that transferability is reliable. And it actually turned out while you can train on one detector and transfer to another, it's very unreliable, and we don't have any understanding of why it transfers in some situations and why it doesn't in others. One thing that does transfer very well, though, is that the data set you use to create the pattern doesn't really matter. So you don't need to create a particular data set in a particular domain to create such a pattern. You can use a COCO data set. You can use a number of other person detection data sets, including some much older and smaller data sets, and they all work equally well. But for this to work, it seems like you really have to target a particular detection architecture.
Interesting work. Let's talk a little bit about some more recent work. You published a paper relatively recently around watermarking for large language models. Tell us a little bit about that, the motivation for that work, and it's a little bit about its setting.
Yeah. So what I'm really interested in is preventing potential future malicious uses of language models. One thing that I think has really made the rounds on the internet is people concerned about the use of large language models like ChatGPT for cheating on homework assignments. I know at University of Maryland, people are very concerned about that. We even had training sessions. That's actually not so motivating to me. What I'm more motivated by is the use of chatbots to operate social media bots, so create sock puppets on social media, which potentially, I don't think we quite know what the future looks like in terms of adversarial uses of these kinds of platforms. But it's certainly possible that you could use a chatbot to operate a large fleet of social media sock puppets and use it as for a social engineering campaign, for example, to try to engage in election manipulation, to try to promote a conspiracy theory. And something like ChatGPT is so powerful that you can definitely create different bots that inhabit different personalities and personas, and might potentially be very difficult to discern from real people. And from what we've seen in the past, these kinds of social engineering campaigns can potentially be very damaging. And so, to me, that's the most motivating reason to have something like a watermark.
So along those lines, I've seen some really interesting thought pieces that kind of conjecture that Chat GPT and more specifically, low quality, artificial, and potentially, untrusted or bad intended content, will be the downfall of the internet and kind of push us all away from, trusting it and other things, people that we, supposedly people that we connect on it, pushing us away from that and more towards kind of old school, person to person connections through, validated
Yeah,
networks.
you make it sound kind of nice, huh? No, if we if no, I agree. I think there's as it could having this kind of synthetic content out there might devalue the internet in a lot of ways. One thing that it might affect a lot is also just email communications. That's one motivation to have a watermark, even, is to be able to filter out things like automatically generated communications uh, via email, right? Synthetically generated blogs, synthetically generated emails. It has a potential to make the internet into a much noisier and potentially less pleasant place.
Yeah, yeah. And so the idea with this project is that you show that without changing the meaning, you could inject some kind of watermark into generated text that was later detectable.
Yeah, so that I could say a few things about how such a watermark would work. But the idea is that we can make very subtle changes to the patterns that a language model uses in its speech, and those patterns can be detected in such a way that with a relatively short uh, span of text, usually say a few dozen tokens, you can oftentimes detect with very very high confidence. So both a low false positive rate and a very high sensitivity, you can oftentimes detect AI generated text if it is watermarked. And the way that such a thing might work is that every time a word is generated. So a little bit of background. Large language models, the way that they typically work is they generate text one word at a time. You give them a prompt, and then they will continue from the prompt by generating text one word at a time. Uh, Language models also have what's called a vocabulary, which is the list of all words that they can output at each time step. And the way that the watermark works is that when before it outputs a word, we take the list of all possible words that could come out of the language model, and we randomly partition it. We pseudo randomly partition it into a green list of good words and a red list of bad words. And we give the language model a reward if it's able to use one of the good words. So it's able to use one of the green list words. And so if you say that you do this partition randomly, if a human is typing, every time that they type a word, you generate a new red list and green list. And if you generate those lists randomly, then half of the words that a human types is going to be green, and half of the words that a human types are going to be red. But if I give a chatbot an incentive to use green list words, then a larger proportion of the words that are used by the chatbot are going to be green. And so by just counting how many green list words are used, you can identify the difference between AI generated text and human generated text. If there's a very large fraction of green list words, then it's almost certainly AI generated text. And by doing some statistics, we can actually quantify exactly how confident we are that it is AI generated.
You described the creation of these lists as pseudo random. Um, can you characterize the creation of the lists a little bit more? I guess one thing that jumps out at me is that if it's truly pseudo random, there's the potential that you can't express a given concept or idea without using one of these one of the words on the red list, for example. Like, how does the method protect against shifting the meaning that the LLM generates?
So the way that this works is every time you type a word, that word that you just typed is used to update the red list and the green list. So when you type a word, that word is used to seed a pseudo-random number generator, and that generator produces a new red list and green list that are applied to the following word. So every time you type a word, the red list and the green list changes. An important thing about that scheme is that after the text is generated, somebody else who wants to check for the watermark can use the exact same rule to produce the red list and the green list. So they look at every word in the text, they use it to seed a random number generator, and they produce the red list and the green list for the word in front of it. So after the language is generated, it's very easy for someone to come back and count how many green list words there are. And an important property of this watermark is that the method for creating the red list and the green list don't depend on any knowledge of the actual language model. You only have to know the pseudo-random number generator that is used, and you seed it with you need to know the vocabulary, the options that are available in the vocabulary, and you need to know the pseudo-random number generator. And that's important because you want it to be really inexpensive and very efficient to check for the watermark. And you don't necessarily want somebody to have access to the language model parameters to check for the watermark. And so by using this sort of red list, green list scheme, you can create the watermark in such a way that this random partitioning is predictable and reproducible. And it also doesn't require you to have any knowledge of the language model parameters, because very often these language models will be proprietary.
So, along the lines of this distinction between proprietary language models and a model that you would have access to, is the entire method something that can be bolted on to a proprietary black box language model? Or do you need, you mentioned earlier that you're tweaking the reward function to give the language model a reward for using a word on the green list? That to me implies that you have control over the language model itself.
So one nice thing about this watermark is it's fairly easy to, as you say, bolt it on to any conventional language model. As the language model is choosing words, you just provide some incentives for it to use green list words. So you take there's usually logits or probabilities that come out of the language model, and then you make small changes to those word scores or probabilities before you choose which word to use from that list. One thing you asked about is, doesn't that prevent you from being able to say certain things? So the way that this works is we provide a little bit of reward for the model if it uses a green list word. But if there's a word that it's very confident that it wants to use, that reward is not enough to override that choice. Right. So for example, if you say Barack and then you want to follow that with the word Obama, in a language model will probably be very confident that it wants to use the word Obama after Barack, because in most Western language corpuses, that probably almost Obama probably almost deterministically follows the word Barack, and so the scores for that word will be very high. Now, when we'll add a little bit of bonus to the scores that come out of the language model for other words, but that won't be enough to override the fact that Obama is still the most likely word to be chosen. So what we actually do in our paper is we analyze what we call sentence entropy and token entropy. So there are certain tokens that we say are high entropy tokens. Those are basically words that the language model wants to write where it has a lot of choices that it can choose from. There's a lot of good choices. So you may say, today, I feel, happy, I feel elated, I feel fantastic, right? There's a lot of different choices of word that you can make that are all functionally the same. And very often the language model will output almost identical scores for all of them, meaning that the language model is indifferent to which choice you make. And in those sorts of high entropy situations, the watermark will be very strong. So it will fairly strongly enforce that you have to choose something from the green list, because that doesn't really cost you anything. You have a lot of green list choices and a lot of red list choices. And if they're all equal, you might as well just choose something from the green list. But in situations where the model is very confident, so in a low entropy situation where the model is very confident of the word that it wants to use, the incentives that we apply don't really change the language model behavior at all in those situations.
What's the typical vocabulary size for a language model?
So it really depends on the language model. Most language models have a vocabulary of about 50,000, and that's about the size of GPT's vocabulary, which, as far as we're aware, is still the same vocabulary size that they're using for ChatGPT. There are models with much larger vocabularies. So the Bloom model has about 250,000 words in its vocabulary, which is quite enormous. But because there's so many words in the vocabulary, that's one of the reasons why a language model like this works. There could be many, many different choices for which the model has comparable scores. It doesn't have any strong preference between them. And by picking and choosing the situations where you want to enforce this watermark, this green list behavior, it's possible to inject this watermark without having any significant impact on the quality of the text that comes out of the model.
Is the relatively larger size of the Bloom vocabulary due to the multilingual nature of that language model?
Yeah, my understanding is because it's multilingual. It crosses over different alphabets, different languages, and they just want to make sure that they had good word representations across different languages.
And so the method, I guess I'm the way you've described it, this is something that you do need to kind of control the language model in order to implement. I'm curious if you've explored, is there a way to implement this at the prompt level? Like use one of these words, you prepend the prompt or something like that with extra points if you use one of these words.
That's interesting. Actually,
Could something like that
huh.
conceivably work?
We haven't really thought about that, but conceivably it could work. If those words were, the question is, how would you generate those words, right? One of the properties of the watermark is you want to make sure that you have something that is really invariant to human behavior. The way that we use this random partitioning between red list and green list words, it sort of guarantees that a human is always going to use a 50-50 red list, green list split, at least an expectation. So if you were to pick the words that you put in the prompt, the question is, how would you choose those? If you chose words that maybe a human is likely to use, you might run into a situation where you can't discern between human and machine behavior.
Yeah, I'm envisioning a scenario where you've got, some front end in front of like a chat GPT, or some other language model. And the human puts in their prompt, and then you, after, their prompt, you kind of pass that along with something before or after this is. And constructing your response, you use a word from this list. So you'd have the human aspect of it, and then you'd have the list that you create in a similar manner to what you've described.
That is interesting. I could actually conceive of a way that a situation where that might work.
Okay.
Like you could inject something into the prompt, and then you can detect later whether it's been injected. I haven't seen anything like that studied, but it's totally conceivable that you could construct a watermark that way. One of the things you have to keep in mind, though, is one of the nice things about the watermark that we proposed, it does this word by word watermarking. You want a watermark that is robust to situations where only a chunk of text that is inside of a document is watermarked, or situations where somebody slices and dices and edits the output from a language model. You still want to be able to identify whether it's watermarked. And in situations where the watermark for a large block of text depends strongly on what came before it, you could have a situation where you can't really identify how to detect the watermark. If someone, say, excises a chunk of text from a GPT conversation, you don't necessarily know what came before it. And so you might not be able to know what the prompt was and what generated the watermark. So the question, it's actually, I think it's really important that you have these kinds of properties. You want to be able to detect if only a chunk of a document is watermarked. Otherwise, there are use cases where the watermark might become undetectable. But also, one thing we're concerned about is we don't want it to be too easy to attack this watermark.
Right. That was my next question.
Yeah, a lot of people on Twitter, when they saw this watermark, their first reaction was it's very easy to just remove this watermark in various ways. And I actually don't think we're still doing work on creating watermarks that are more resistant. You can design detectors that are more resistant to attacks than the simple detector that we put in our paper. But in general, removing the watermark is not as easy as people have made it out to be.
What's the typical rationale? That is not intuitive to me. If you're kind of dynamically generating these red and green lists, with every token, what's the rationale for being able to easily remove the watermark?
I think the thought that people have is that if you just rewrite the language with either by hand by a human or with a different language model, because it's written exactly that, because it's written now by an agent that is not watermarked, you wouldn't be able to detect the watermark anymore. It turns out removing the watermark is not quite that simple. Research on how hard it is to remove the watermark that way is ongoing, but it's not as simple as people make it out to be for a couple of reasons. One is that available summarizers, at least the state of the art summarizers, which are currently proprietary models, they have a strong tendency to repeat sentences and sentence fragments from the original text. Now, the watermark detector is very, very sensitive. So, like in our paper, we gave an example where we provide 24 words, which is a moderate length sentence, and we can already detect that it's watermarked with a false positive rate of 10 to the negative 14. So pretty high confidence detections, right? The watermark is extremely sensitive. So if you were to use something like the Da Vinci summarizer to summarize the text and hope to remove the watermark, it would still be detected if Da Vinci, say, kept in some half sentences or some phrases from the original. Now, we haven't done a thorough study on how often this happens, but in my experience, especially when you have a long fragment of text, it's pretty consistently the case that Da Vinci will recycle phrases from the original text and use them in the summarization, in which case the watermark would not be removed. Then there's also the issue of human intervention, right? A human could go and rewrite the document. I'm also interested in how easy or hard that is. Something to keep in mind is that if a human were to rewrite the document, but they were to reuse the same bigrams that appeared in the original document, so let's say that they are slightly more likely looking at one document and rewriting it and summarizing it in a different way. If the bigrams, which means sequences of two words that appear in one document, are recycled and placed into the human written document with some greater than zero level of regularity, then once you acquire a long enough fragment of text, the watermark will actually still remain detectable. And sometimes that can happen if you're just copying entire words. So there are actually many human words that are actually broken down and written as multiple word fragments. And very often the watermark will choose to use English words that are actually compound. So they're written by multiple word fragments that are all on the green list. And so when you choose to use a word from the original watermark writing, if you recycle that single word and use it in the human summarization, you're actually increasing the green list rate. And if you do that enough times, the watermark will ultimately become detectable. So it's not to say that the watermark isn't removable. It certainly is. It's just not as straightforward as people have made it out to be on the internet. People say, well, this is trivial. You just take your GPT text, you just put it through a summarization algorithm, and poof, you're done. But actually, it's with the summarizers that are available today, it's very unlikely that that would work consistently. Now, it is possible that if you had low level access to a powerful language model, you could force it to unwatermark the text in the same way that I force a large language model to watermark the text. So you could engineer a system, but to do that, you would have to have white box access to a very powerful language model that can produce very high quality text. And right now, I don't think the open source language models are anywhere comparable to the power of the proprietary language models. We actually, in our paper, we experimented with using T5, which is a pretty powerful open source generative model to do an attack like that. And we found that the quality of the text you get degrades a lot when you use something like T5. It's just the open source models are nowhere near as powerful as the proprietary models.
That specific attack is taking the text that's generated from the LLM that uses watermarks and using another language model to summarize it?
Exactly. So what we do is not necessarily summarize the entire thing, but we take watermark text generated from a watermark language model, and then we take the T5 model and we look for spans that have a large number of green list tokens. So remember, watermark text has a lot of green list tokens. The way you remove the watermark is you try to inject a lot of red list tokens. And so what you can do is you can take spans in the text, and then you can ask T5 to rewrite those spans for you and then replace them. So it's not using it's like a summarizer in the sense that you give it the entire document and ask it to regenerate the entire document. There aren't really any great open source implementations of that, but using the open source models that we have, we can at least rewrite spans of text or rewrite individual sentences, and we can do summarization at that level. And if we do that to enough of the sentences, you will eventually remove the watermark. But with the open source models that are available today, there's a very large quality degradation that you have to be willing to suffer in order to do that sort of attack. There's always a trivial way to remove the watermark. Right? People always ask, is the watermark removable? Yes, absolutely, the watermark is removable. There's a trivial attack on the watermark, and that's that you just replace the watermark text with random tokens. Just replace it with random characters, right? And that won't be watermarked, right? But the point I'm trying to make is just that it's always possible to remove the watermark. The question is not whether it's removable. The question is how much of a quality degradation will there be when you remove it. And now today, the publicly available AI models that you could use to remove the watermark in a really precise way, in a really effective way, just aren't nearly as good as the proprietary models. And I would expect there to be a big quality degradation if you were to use them to remove the watermark. Now, there are amazing proprietary summarizers like the DaVinci Summarizer, but those tend to preserve things like sentence fragments. And so they are very likely to preserve the watermark. And we don't have control over them because they're proprietary, they're not open source. Over time, there will likely be more powerful open source models that become available, and that will make it easier to attack these watermarks over time. But as it stands today, I actually think it's quite difficult to remove the watermark in an effective and fully automated way.
And when you say the DaVinci Summarizer, is this using the DaVinci GPT-3 as a summarizer?
Exactly. Yeah. This is the DaVinci is one of the APIs provided by OpenAI. It's one of the ways you can access their GPT-3 model.
Yeah, this is making me want to pop open a ChatGPT window and give it a random or give it a paragraph and say, rewrite this paragraph, preserving meaning and using none of the same words. Have you tried that? Like, how close will it get, do you think?
That we haven't tried that particular attack. We have tried a number of attacks. So there are attacks that you can use. We call these in-context attacks, where you specifically instruct ChatGPT to do something strange that will invalidate the watermark. In fact, there's a whole slew of attacks that we discuss in the paper. One of the in-context attacks that we do discuss is what we call the emoji attack. This is something that was actually proposed on Twitter originally. And what the emoji attack is you ask a question and then you say between every word, after every word that you output, insert an emoji. And it does that. So it will answer your question, it'll produce the text you wanted. And between every word, every pair of words is an emoji. Then you take that text and you remove the emojis. And when you do that, it changes the red list and green list for all of the words that come after the emojis. Because those emojis were used to seed the random number generator and produce the list for the word that comes in front of it. So there's a range of in context attacks like that that could be used. Right. In order to prevent those, if what someone were to implement the watermark, you would have to filter out those kinds of malicious queries. I don't think it's unreasonable to expect to filter out those kinds of in context queries, because there's already a lot of queries that are considered malicious and are filtered out. But this is another category. These sort of in context attacks on the watermark. It's another category of queries that would have to be detected and filtered, on the server side.
Interesting. Interesting. Where do you see the watermark research going?
I think there's actually a lot of future directions on watermark research. You could think of more effective ways to embed the watermark, so you can get more watermark strength with less, without risking so much degradation in text quality. Right now, there's sort of a knob you can turn. You can choose how strongly you want to enforce that it uses green list words. And we generally use a very gentle enforcement because we don't want to have a noticeable degradation. But you might be able to come up with more sophisticated rules that can pack more green list words in without, maybe more sophisticated rules that pack in more green list words without a quality degradation. And then the other question is, how can we build more sophisticated detectors? So if somebody were to upload, text that someone were to provide text where only one or two sentences instead of a very large corpus is watermarked, you could potentially detect that by doing a brute force search and just looking for the watermark on every sentence in the document. But there are probably much more effective and much more computationally efficient ways to detect the watermark. So you could look at different kinds of detectors that have very high degrees of resistance to things like summarization attacks, or detectors that are very resistant to things like human rewriting. And you can also look at computationally efficient detectors. So you might want a streaming algorithm, something that just accepts one word at a time and does a small amount of computation. And then once it's streamed over the entire document, it tells you whether or not it contains the watermark. So there's a whole bunch of different directions that you could go in terms of developing different kinds of algorithms. And one of the reasons you might care about these detectors is not just because you want to be able to remain sensitive to the watermark under different kinds of attacks, but also you just want it to be very computationally efficient to check for the watermark. It might be the case that a social media platform wants to scan everything. Let's say Twitter. One of the interesting things about this watermark is it actually is sensitive enough that you could detect it with high confidence from a single tweet. But if someone did some sort of simple attack, you might need to, you could do something like concatenate multiple tweets and then detect the watermark. But it might be the case that you might want to monitor users. You might want to check for the watermark in different users when, say, people tweet or people upload a post to Facebook, just to be able to monitor accounts that are likely to be a bot. If there's a large amount of watermark text coming from a user, it's very likely that that's a bot. Right. But in order to do that kind of monitoring, you hypothetically want to be able to run a watermark detector on all of the text that comes in, right? On every tweet, on every Facebook post. And so in order to be able to do that at scale, you want to have very efficient algorithms. You don't want to have to do a brute force search where you run the detector on every subspan of text individually inside of a document. You might want really efficient streaming algorithms. And so I think there's a whole there's a whole subfield that you could even imagine of algorithms research where you focus on efficient detectors that are very remain sensitive under different kinds of attack methods.
Have you thought much at all about the kind of broader political, economic incentive structures around the adoption of watermarking technologies around LLMs?
Yeah, I have. So there's a few different reasons why an organization might want to adopt an LLM. Now, there are reasons why adopt a watermark, and there are reasons why they wouldn't. There's a lot of money to be made selling high quality generated text to malicious actors, right? So why would you want to have a watermark that prevents people from doing that? And I think there's a couple reasons. One is that I think the large companies that create these high quality models, and right now creation of a model is very expensive. Large companies, I think they want to have a socially responsible appearance. I think maintaining social responsibility is a goal of an organization like OpenAI, at least one of their goals. And I don't think that they want it to be perceived that their product is being used for all sorts of malicious purposes like spam, social engineering attacks. I think it's just very bad for the public image. But also, I think it potentially it raises the risk of some sort of government regulation against them if their products are being used almost exclusively for negative purposes. And so that's one reason why there might be a financial incentive to watermark. But there's two other incentives that I think are interesting. Um, One of them is that it may be that in the future there's a lot of LLM generated text on the internet, and when you train a language model, you want to be able to exclude it from your training set. And in case that sounds ridiculous, I would point out that this has already happened actually with OpenAI's Whisper model. There's the Whisper model is a model that does speech to text transcription. And in order to create a data set for this, they searched the internet for speech with accompanying transcriptions. But what they found is that a very high percentage of those transcriptions were already generated by inferior models. And training on those inferior model transcriptions, you're never going to get a model that's any better than the lower quality models that existed before you. And they actually built an entire pipeline to use various methods to detect and remove AI generated transcriptions in order to be able to create a good data set. So I think that this is looking a bit, off into the future, but there are incentives for language model companies to want to be able to detect the presence of their own, uh, text. And then finally, the last incentive that they might have, and I think maybe this is the greatest incentive, is you could sell API access to the detector. Right? This is another service that you can charge for. And in our paper, we actually talk about how you can have open source detectors that anybody can run locally. And then we also talk about how you can have closed source detectors and various cryptographic considerations you'd have to consider to make it very difficult for someone to extract the watermark algorithm. And in that case, a closed source detector, it's not only very difficult to attack the watermark because you don't actually know which words are red listed and green listed. It becomes much more difficult to attack the watermark if it's closed source. But also, like I said, a company like OpenAI could potentially sell API access to.
Trying to defeat or attack the watermark. Have you looked at watermark, just watermark detection? And the thought that I'm kind of thinking about is like, given the example that you provided with Whisper and OpenAI's, they're certainly thinking about, hey, if we, quote unquote, pollute the internet with all of this chat GPT and GPT-3 generated text, and then we want to train GPT-4, how do we detect it? Um, you know, do we know if they've already implemented some watermark algorithm?
It's hard to know. It's really hard to know. I kind of doubt that they have, only because they have said publicly that they're planning to implement a watermark. And I think it's likely to be very similar to the watermark we describe in our paper, just based on the information they have released. I think that they've been pretty transparent.
But that suggests that that watermarking, a la what you've done in the paper, it's not easily detectable statistic just by running statistics on text.
I think it would be very difficult to detect it by running statistics on the text. If you had access to the language model, you might be able to, because with the language model, you know exactly what ordering of words it prefers. And if you detect that it deviates from, if you know what language model was used to generate the text, you might be able to detect that it's deviating from the non-watermark predictions. But I think you would have to know a lot. I think it would actually be quite difficult to detect the watermark. Yeah, but is there already a watermark present? It's something like a Chat GPT. It's possible, but so far, OpenAI has been pretty transparent about their efforts to create a watermark, and pretty transparent about their efforts along the lines of synthetic text detection. They actually have their own machine learning based detection tool that is available as sort of a beta test right now. And so I guess I don't see any reason to. I would speculate that they probably haven't implemented this yet. It seems like they've been transparent enough that we probably have heard about it.
Yeah, no, the bigger question that I was getting at was detectability using statistical methods, and it sounds like it's hard.
Oh, I think doing it with statistical methods is difficult. One thing that a related topic is actually detectors. For example, there's this GPT-0 detector. There are machine learning based detectors that will just look at patterns in the text and try to identify whether or not it is AI generated or non-AI generated. Those are just based on statistics. They just look at simple statistical metrics that you can compute on the text. I'm not aware of such a statistical metric you could use to detect the watermark, but that doesn't mean that someone might not develop one. There's clever people out there. Somebody might develop a statistical method that exploits that.
So, switching gears a little bit, you've also done some work looking at accidental data leakage from models like Stable Diffusion. I think by the time this podcast comes out, my interview with Nicholas Carlini will be published, or shortly thereafter. So maybe talk a little bit about that work, and I know you're familiar with Nicholas's work. How it might contrast with what the audience has previously heard about in that vein.
Yeah, so I actually, while we were both working on these projects, I was in communication with Nicholas Carlini about the various things that we were working on. I think we're both working on some related topics. Nicholas's work is focused a lot on ways that you might deliberately extract data from a diffusion model. And I think this is really topical for Google, which is the institution that he works for, because they have diffusion models and they've wanted to release them in the past, but there's always this concern that somebody might be able to extract the training data, and it's not necessarily clear what the licensing terms or the privacy terms are that data should be subject to. And so this has been really difficult for them. I think it's become a very salient issue recently. In the past, Google's been very conservative about the models that it's willing to release because they perceive there as being these sort of data set risks. And when those risks are present, they usually default toward not releasing a model. But now with Microsoft hot on their tails, releasing all of these interesting AI products, I think that there's a lot more pressure on Google to try to release its own suite of models. And so I think the onus is on them now to try to find ways to clear these risks in a responsible way, rather than just perceiving that there is a risk and then moving on. So I think we need to find ways to be able to identify when these risks are present. But Nicholas's work has largely been focused on ways that you can deliberately extract data from models. Whereas our work is focused more on whether this sort of data can reemerge by accident. So if you're just using a diffusion model and you happen to be, type in some prompt and you press enter, what are the odds that the image that it produces for you is actually going to contain pixels that are more or less copied and pasted from the training data?
That sounds like another key difference between your work and Nicholas's. His tends to focus on the models reproducing more or less entire images that were in the training set. And it sounds like you're looking at, you said pixels, so your bar for leakage is different than his.
Yeah, so we look a bit at whole image replication as well, but a big focus of our work was that very often you see an image that, according to whole image metrics, if you measure the similarity of a whole image to images in the data set, it doesn't necessarily find a match, but looking at it, it seems like there may have been something stolen. Like you see some crystal clear, very photorealistic object that you would expect to appear in the real world. Um, and so one of the things that we did in our work is we started out by just building a pipeline for partial copying detection. So we wanted to have metrics that could detect whether two images share something in common. It doesn't have to mean that the whole image is the same, but maybe an object in the image overlaps. And so we did a large study of looking at different kinds of metrics that we could use to detect this kinds of partial copying. So copying where just a single object or a background is replicated, but the entire image is not replicated from the training set. And then we deployed those kinds of detectors on different diffusion models. And actually, at first, we found that the diffusion models we were experimenting with weren't copying from the training set. We started by looking at ImageNet latent diffusion models. So diffusion models that are trained on the ImageNet data set, and they're not text conditional, which means you can't give them a prompt, but you can give them an ImageNet class. So for example, one ImageNet class is bananas. And you give it that conditional class, it'll generate a picture of bananas. And we did a large study on this ImageNet model. We started with that model because it's smaller than Stable Diffusion. And looking at that and a number of other models, we didn't observe any copying from the training set. And we thought maybe this wasn't such a big issue. And so we actually wrote a paper that said that explained our methods and said we didn't find any copying in these data sets. And we completed that paper about a day before the CVPR deadline. And then that evening, we were waiting for our results to come in on Stable Diffusion because we wanted to add that to the paper before we submitted it. And then, lo and behold, about midnight, the day before the deadline, I get a Slack message from my student where she sends me this interesting photo where there's a prompt you give it that asks for a picture of a cell phone case with an image from New Orleans on it. And it generates that picture of a cell phone. And then we find a match in the data set that is the exact same background, but a different cell phone. So what the model did is actually replicated pixels. Basically took an image straight out of the training set of a cell phone case, and it just ripped out the original cell phone case and it put in a different cell phone case. And as our script ran, we started finding more and more of these examples where it was replicating content from the training set. And eventually we had a lot of these examples. We actually sort of scrambled and rewrote the section, had to go into sort of code red to update our paper to include all of these new results. This is sort of the publication deadline life of an academic. Um, yeah, but it was really interesting to see the results that we got. Stable diffusion behaves very differently from other models. It definitely seems to exhibit these kinds of replication behaviors that other models don't. It doesn't do this all the time, at least not as far as we can tell. In our experiments, this happened about 2% of the time. We are repeating some of our studies now using a data set that is available of actual prompts that people input themselves. Our original study, we used prompts that we just took. We took captions off of images from the Lion data set, and we use those as prompts. So we're essentially using prompts from the data set when those are more likely to elicit data replication from the data set than a random human, user generated prompt. And so we're completing a study now where we look at this data set of prompts that were input by actual people and seeing how often replication occurs. And we don't have hard numbers on how often that happens, but we do still observe situations where this kind of replication happens. And it's, stable diffusion is really different. It's really different than other models, and there's all sorts of reasons why that replication might be happening. It could be because of repeated images in the data set. And one of the things that Nicholas did in his paper is he actually has a histogram that shows how often images are repeated in the data set. And there are images that are repeated thousands of times. And so this image replication could be one of the reasons. But I think that there's much more complex reasons than that. And so this is work that's still ongoing. But I think it actually has a lot to do with the properties of text conditioning as opposed to something like class label conditioning that you might do with ImageNet. And I think that text conditioning makes it much more likely that these kinds of replications occur. But that, I say that it's a little bit speculative right now. Research is still ongoing.
In your detection pipeline, were you taking an image or an entry from the Lion data set and its prompt, and then feeding that prompt in and comparing the resulting images to the image from the data set, or did you process the entire data set in some way?
So what we do is we actually pre-process the data set by extracting feature vectors from it. And then we generated many, many images. So we'll generate tens of thousands of images from different randomly selected prompts. And then we'll extract a descriptive feature vector from all of those. And then we go back into our database of data set features and we try to see whether they match up. Right. But you have to do this very efficiently. Our original study actually only looked at a 12 million image subset of the original training set. Our more recent studies are going to look at the entire 2 billion image training set for the original Stable Diffusion 1.0. And you have to be very efficient. It turns out 2 billion images is a lot. You have to be very efficient about how you store those feature vectors and how you pre-process the data set if you want to be able to scale up to that size. In fact, just getting access to the images, we actually knocked over the DNS server for our entire institute. We made so many queries to different web addresses trying to get access to 2 billion images that actually overwhelmed the entire DNS service for the chunk of campus that we're on. And we got a very angry email from our IT services about it. So we had to change our practices to make sure that doesn't happen. But yeah, scaling up the Lion data set is very, very large, and scaling up to training at that size is quite difficult.
Do you cover those scaling challenges, or I guess this is work that's forthcoming? Are you? Well, let me just ask you this: what are some of the ways that you have adapted to this scaling challenge? Any tips for folks that want to try to build something that's working on 2 billion images?
Yeah, well, I mean, the number one thing is it's over time. Our the hardware that we buy at University of Maryland has changed a lot. The use cases have just completely changed as we move into this space where we're using large language models. Over time, as these large language models become publicly available, it actually gets easier and easier for us to do research because there isn't really a reason to train a language model. Sometimes you just want to experiment with them or fine tune them, and so actually the amount of compute that you need to do these experiments could be quite small. But the problem is just loading models can be very difficult. Storing large data sets can be very difficult. And so suddenly we're making a lot of hardware investments in very high memory GPUs, in very large data set storage systems. And these are things that we didn't really need before. We used to be, 3, 4 years ago, we were training small models on fairly conventional GPUs. We were just using, the ImageNet data set was pretty much the biggest thing we would have to poke at. Um, in the last 2 years, it's just been a complete 180 in terms of the hardware requirements. And we're constantly running up against problems that test the limits of what we can do, but in completely different ways than what we used to see. It used to be that you're kind of limited in the amount of compute, just the amount of flops you could crank out to train models. And now we're just limited in the amount of the size of the model that we can fit on the GPU, the size of the data set that we can store. It's completely changed the way that we think about building out our hardware infrastructure.
Well, Tom, thanks so much for taking the time to share a bit about what you've been working on.
Yeah, thanks for having me. I really appreciate it.
Thank you.